All right, here's our video, time dilation and the Lorentz factor. And we'll be using some math, not so hard. So anyway, what time dilation is how time appears to pass differently for any two people, two observers. Or a simple explanation is the faster you can go, time will slow down. And we'll explain that in the video. And it happens with GPS systems, GPS that tells you where to go in your car. In the GPS system, time is slowing down, and they have to consider that because they're going so fast. But it's really almost insignificant for us. But for the GPS system, it's important, right? So, it wants you to turn left at a certain time, right? So anyway, the time dilation is only 38 millionths of a second. But again, we'll explain that with doing an equation and so forth. And what you're seeing here, this little thing looks like a Y. It's actually the symbol gamma, a Greek letter gamma, and the lowercase gamma. And it represents the Lorentz factor. In other words, so we're going to get this time dilation number, and I'll explain it. So let's get a clean page. So let's write out the equation. So, and what should we use? Maybe we'll use red. Red works. So I'm trying to create this gamma symbol. Not doing a very good job at it. It's not supposed to be a Y. It's supposed to be gamma, the gamma symbol. And of course, it's the Greek letter. And that'll give us our time dilation. And what we'll do is we'll do 1, and we're going to divide it by the square root of 1 minus v is velocity, and c is the speed of light, and we want to do that squared. And by the way, so again, v equals velocity. Remember, velocity is just the rate. It's the speed with direction. And c is the speed of light. You're wondering why they use c. Well, it's a Latin word. In Latin, it comes from a Latin word, celerity. And celerity just means swift. So we're using a Latin word for the speed of light instead of L, right? Remember, science is not just English. There's many languages in the world, and that's why Latin was used a lot in science. All right, so we have, this is the equation, and it may seem complicated, but let's try something. Let's say that you were in a spaceship. And by the way, one thing we should know is that no one could go at the speed of light. Like, the speed of light is the universal limit. So if you had a speed limit sign, the speed limit, we'll say, here's the speed limit. And I put a C. Speed limit is C. Well, that's the speed of light, right? And no one could get there except photons and perhaps gluons. But anyway, let's say that you're in a spaceship and you can't go the speed of light. You can only go 80% the speed of light. What will happen? Well, first of all, what would happen with photons do this? Look what happens. There's going to be something interesting if we put photons in this. We're going to do 1 divided by the square root of 1 minus. So the velocity would be the speed of light. And if you can probably see what's going to happen now. So c over c, it's going to be the same rate. That just becomes 1. So you're going to get this. And you're going to see there's a problem. 1 minus, and 1 squared is 1. You see the problem? You're going to get this. And that's a big problem because that's undefined. You cannot have 0 in the denominator. It's undefined. So from this very equation, if we plug in the speed of light, that means we get something that's undefined, which tells us that light, if you go with the speed of light, time doesn't exist. In other words, photons don't experience time. That's the wild part of this equation. All right, so let's clear that out. Use another color. Write the equation again. Let's try blue this time. So again, let's try to make a better gamma. Something like that. We'll just use that. So 1 over the square root of 1 minus, and we're going to use velocity over speed of light squared. We already said that if we plug in the speed of light, we get undefined. which means that photons, which are light, photons do not experience time. Seems very strange. In other words, if we see a photon, if we see a photon's coming in from the sun, it takes 8 minutes, 19 seconds for that photon to reach us from the sun. It's we're looking at that as 8 minutes and 19 seconds. For the photon, though, it would be no time at all. It's hard to wrap your head around that. So let's now say that we're in a spaceship and we're going 80% of the speed of light. And we're going to use, and remember, the speed of light is 186,000 miles per second. That's what the speed of light is. So if we say 80%, we're saying our velocity would be 0.8 c. 80% the speed of light. What happens if we plug that in? And also for this equation, and let me just use another color, we, instead of using feet, because that's miles per second, we're going to use meters per second. So in meters per second, it's this big number here. So we'll say meters per second. So our answers will be that. So what if we're trying to find the time dilation if we're going 80% of the speed of light, which we can't even get that speed either. We can't even get 3% the speed of light. Nevertheless, let's plug it in. And let's keep purple. Get a little space for it over here. So we're going to say gamma, not y, is going to be 1 over the square root of 1. Now our velocity is going to be 80% of the speed of light, so 0.8 will be our velocity. And by the way, that would come out to be, and if you do all this math, it'll be this. I'll write that number down. But you really don't have to do that, and you'll see why in a minute. So that'll be that, and you're going to divide it over the speed of light in meters per second. And of course, all that will be squared. And if you do that, you'll get 0.64. Or you could have just plugged in 0.8, right? So if you do 1 minus 0.8, you will get 0.64. So the time dilation, if you did that, will be 1.67. And what does that mean now? What do you think it means? Well, it means that if you went out at the speed of light, first of all, we have to throw in a time to it. So if we throw in a year, we'll just times that by 1 year. We have to also put time, right? So if we throw in time, and we'll say the time is 1 year, it'll be 1.67. That means that when you went out in space and you came back on Earth, you went 80% the speed of light and you came back, you did a round trip going 80% the speed of light. You came back, 1.67 years have passed on Earth. 1 year, which is 1 year, 8 months. But in your spaceship, on your clock, it's only been 8 months. So you're off by a year. That's what basically it's saying. You're off by a year and 8 months. So again, 1.67 is 1 year, 8 months, basically. So 1 year and 8 months have passed on Earth, but in your spaceship, it's just 8 months. That's how you look at the time dilation. Let's do a few more. Let's clear this out. All right, so let's say again that you went 80% the speed of light. So we already know that the time dilation for the Lorentz factor, let's get our pen going again. Why don't we stick with that color. So we know that the Lorentz factor was 1.67. So if you spend a year in space, on your clock, a year, you thought it was a year in space, but actually you're 8 months off. But let's say you spent 5 years in space. 5 years in space. So on your spaceship, it's just 5 years. But if you multiply that, you'll get 8.35 years on Earth. And that's just like 8 years, 4 months. So 8 years and 4 months have passed on Earth, but 5 years have passed on your spaceship. So you're 3 years and 4 months off. Right? Just subtract. So when you get back, let's say for example, you're 30 years old. You're 30 years old. You get back when you're 30 years old when you took off. You get back to Earth, and you're 35. Let's say you had a friend who was your same age. Now your friend's saying, "Well, I'm not 35. I'm 38. And 4 months." Think of it as 10 years now. Try it with 10 years. Right? Just times it by 10. So that's all you're doing, right? So you're doing 1.67 times 10. And you get 16.7. So 16.7 years passed on Earth, but in your spaceship, it was only 10 years. So you're 6 years off. That's going 80% the speed of light. Now let's use the Parker Solar Probe. The Parker Solar Probe is the fastest object we've created. We made, right? The Parker Solar Probe is studying the sun. And let's clear this out first of all. And let's try blue now. Let's try green. Why not? The Parker Solar Probe, the Parker Solar Probe, fastest man-made object we have. It's going 0.064%, not even 1% of the speed of light. To tell you how slow we are. Maybe one day we'll get to 1%. So it's going 0.064 the speed of light. Let's get a little darker color. So basically, it's going 425,336 miles per hour. Nothing compared to what photons can do. So if we plug that in to our Lorentz factor, you do all that stuff, you'll get a Lorentz factor of 1.000000102. It's so insignificant. Basically, if you went on the Parker Solar Probe for 5 years and you came back, your clock will be 6 hours off. It's really nothing. Right? You come back and you think it's 12 o'clock. And we're not talking about time time zones or anything like this. You'll be actually 6 hours off in your biological clock, which is nothing. Let's do one more. And of course, the closer you get to the speed of light, even though we can't get to the speed of light because we said it's undefined, let's say you get 99% the speed of light. If you did 99% the speed of light, fix that 9 there, then the Lorentz factor would be 7.0888. And let's say you did that for 5 years. What do you think would happen? Well, if you did that for 5 years, you're basically getting close to 35 years. But on your spaceship, it's 5 years. So if you went 99% the speed of light for 5 years, wherever you were going, you came back, let's say you were 30. Now you think you're 35. But all your friends, they're 30 years older. So now they're in their 60s, and you're still a young 35. All right. That's our video today. Ponder that.